Hi everybody, I have a video and I'll go ahead and put a link to it on the screen right now. I have a video where I show you how to derive the formula for calculating the slope and y-intercept for a simple regression using calculus. If you haven't seen it and you're not familiar with that technique, go ahead and watch that video now and then come back to this one. What I'm going to look at in this video are two special cases. Where what if you wanted to derive an estimator specifically for a case where you know the y-intercept is 0 in a regression, and then we'll look at another case where you want the slope to be 0. What would that estimator look like for a regression? And then we'll test these to see if they make sense. So just to review the standard case for when you're trying to derive the estimators for the slope and y-intercept that minimize the sum of the squared residuals, you want to do something like this. And I'll just go through the beginnings of that just to remind us. So what you want to do is minimize the sum of the squared residuals. And forgive me if I might use some sloppy notation here. I want you to understand what's going on and not have a lesson in notation necessarily. So OLS, ordinary least squares, is the idea of minimizing the sum of the squared residuals. And in the standard case, well, always, a residual is this idea. It's the actual observation of the dependent variable minus the prediction for the y hat I for that particular observation. And so that's what a residual is. We can plug that in for the EI here. And in the standard linear model, how do you get your predictions? Well, your predictions are equal to some y-intercept plus some slope times some value, xi, some value for some observed variable. So, for example, we might be trying to predict your weight, y, with your height, x, and get a prediction based on some y-intercept and some slope of this linear equation here. Now, so again, we'd plug this formula in for the EI, and in that formula we would plug this in for the y hat I. So you would get some equation like this, where we want to minimize the sum of the yi minus the, sorry, my pen is acting up here. I'm going to have to be a little less sloppy here. yi minus the y hat I, but what's y hat I? Well, that's this, b0. I'm going to distribute this minus sign, minus b1x, and I'm just going to say x. Well, I might as well say xi here. Okay, squared. Now, how do you minimize something? Well, you take the derivative of it, okay? So, and when you take the derivative of this, if you were to multiply it all out and take the derivative, or you can use the chain rule, what you're going to get, I'm not going to explain all these steps, you're going to get the minus 2 times, and I'm going to distribute the summation sign here, the sum of the yi minus the sum of the beta zeros minus the sum of the beta 1 xi's. Okay. And you're going to set that equal to 0 since we're using calculus and we're looking for a minimum. Okay, so that's basically the standard case. And well, actually, you would have two derivatives here. You would take the derivative with respect to the b0 and with respect to the xi here. So you technically have two equations and two unknowns. Let's go on to a special case. Some students wandered in my office the other day and they said, oh no, we have this horrible homework problem and we can't understand it. And I said, okay, let me help. What is it? And they said, okay, well, what our professor wants us to do is to go through these same kind of steps here to derive the OLS estimators for a special case. And what they want us to do is a special case where instead of this being the model, they said, well, what if you were trying to use this model, y hat I equals, you're assuming the y-intercept is 0 in this case. So instead of b0, we're just going to leave that out. That's 0. y0 equals b1 times xi plus, and again, the model is that there's some residual, some error over here. What would you do in this case? I said, well, let's just go through the same steps that we're going through anyway, and let's just see what happens here. And so what you do is you still want to minimize the sum of the squared residuals, and a residual is still the actual minus the predicted. Now the predicted is just this thing instead of this thing. So it actually makes our life slightly easier. So let's go over here and do this, and I'll show you what we end up with, and then we'll look at an example to see if it makes sense. So what you're going to do is, okay, let's just rewrite this whole thing right here. And very simply, all we're going to do is we're going to get rid of that part. We're going to get rid of the y-intercept. So what we want to minimize is the sum of the yi minus the b1xi squared. And to minimize that, what we're going to do is we're going to take the derivative, and it's going to look the same. And now, one difference here, when you minimize this animal, to minimize it, you would have to take two derivatives because you have two arguments that you're minimizing this equation with. You're trying to minimize with respect to the choice of the y-intercept and the slope. Here we only have one argument, the slope. And so if we're going to minimize with respect to this, we're going to have one derivative with respect to that variable. So let's take this derivative. And again, I'm going to use the chain rule. Don't worry about details unless you really have to understand this for your profession. Basically, the chain rule, we're doing the same thing. We multiply by the 2, but then we also have to take care of this minus sign. That's basically what we're doing here. So minus 2 times the sum of the yi minus the b, I'll just drop the 1, bxi. And since it's the derivative, we subtract 1 from the exponent, etc. So, and now we're going to set that equal to 0 to find where this equation's at a minimum. Now, we can get rid of the minus 2 because we just divide both sides by minus 2. All right, and that goes away. Now, what you do, and this is weird if you're not used to this. And I'll try to explain this so you can get a feeling for what's going on. Let's distribute the summation sign there, and what we're going to have is the sum of the yi's minus the sum of the beta xi's equals 0. Now, what do you do with these things? Well, here's the trick that you have to use in order to simplify this in this case. Think about, let's take this over here and work with it a little bit. Something we know about the sum of the yi is, what if we had the sum of the yi divided by n? What would that give us? Well, we know that let me change colors here. We know that the sum of the yi's over n would just equal the average, right? So here's a way that we can use that knowledge to simplify this. Let's just divide the entire equation by n. That's legal. Divide both sides of the equation by n. So what are we going to have? Well, the sum of the yi's divided by n is just y bar, the average of the y's, minus, what's the sum of the b times xi's? Well, that's just the same as b times x bar because we're dividing it by n. Same thing here, equals 0. Now here comes the grand finale. What is the estimator that minimizes the sum of the squared residuals when the y-intercept's 0 and you only have this slope here? It's just solve that for b, just like you normally would. B equals y bar, the average of the y's, over x bar, the average of the x's. Now, let's take a moment to see what this is doing and make sure that this actually makes sense. Just 1 second. Let me pause the video. Okay, so remember that our estimator for a situation where the y-intercept is 0 was the average of the y's over the average of the x's, and I just want to see if that makes sense to you. So let me draw a line here. Suppose our true model is this line. This is our true equation that, and the equation that I have just drawn here is y equals 3x. Okay, I moved things around there. Hopefully that'll be a little bit easier to see. So if our estimator is the slope, the best estimate of the slope is equal to the average y over the average x's, let's imagine that we had some points here and that we collected for data. So let me put a point here and a point here. I'm just making up some data that we may have collected that may follow this general model here, okay? And so with these 5 points, if we take the average of the y's and divide it by the average of the x's, are we indeed going to get a slope somewhere close to this line's slope, which is a slope of 3? Well, let's see. Let me add up all the y values here and get the average. So this y is 6, 7, 12, 15, and 18. So let me get the average of those there. 6 plus 7 plus 12 plus 15 plus 18 equals, so that's a total of 58 divided by 5 points equals, okay, so that's 11.6 for the average of the y's. Now let's see what the average value of the x's is. Well, let's see. We have a x of 1, 3, another 3, and a 6, and a 5. So that total is 18 divided by 5 points, 3.6. So 11.6 divided by 3.6. Let's see what we get. Divided by 3.6 equals 3.22222. Well, it seems like it kind of works. And now you can kind of see how this estimator would work. And again, this only works for models where we assume that the y-intercept has to be 0. So that's why I drew this line going through this y-intercept down here of 0, 0. Now, let's look at one other special case real quickly. This will only take us about 1 minute to do. What if, let's go back to our document here. Okay, so what if, let me move down to a new space here. What if we wanted to, well, I'll go back to the old here. What if we wanted to do, ask the question, what is the best estimator for a case where instead of the y-intercept being 0, what if the slope was 0 instead? What would you do in that case? So here we're going to, instead of calculating our residuals, we're going to calculate our residuals this way, but instead of the predictions being b0 plus b1x, or even saying the y-intercept is going to be 0, now we're going to assume that the slope is 0. So what would we do in this case? Well, let's look at this situation briefly, and I think you'll be able to see how easy this is going to be. Now the estimator is just yi equals b0 plus 0xi, so that part's going to go away also. So let's plug in here. The y hat I now is just going to be some kind of y-intercept. Now, to minimize the sum of the squared residuals, it's going to be yi minus, let me see if I can erase this over here, so we can do this real quickly. Okay, yi minus I'm trying to change color here, b0, yi minus b0 squared. When we take this derivative, we're going to get, let me erase this a little bit more so you can see what's going on. B0, we're still going to bring down the 2 and the minus sign, but then that's going to go away because we can divide both sides by the minus 2. And now we're going to distribute the summation. We're going to have the sum of the yi's minus the sum of the, all right, let me erase again here, sum of the b0's. And now, just the same way we did before, we can divide everything, both sides by n. And what we're going to end up with here is the sum of the yi's over n, which is y bar, minus the sum of the b0's. Here, this is a little weird, but we're going to be adding up the y-intercept n times and then dividing it by n. All what you're going to end up with there is just, sorry, I'm accidentally erasing some things there that I shouldn't. Y bar minus the y-intercept equals 0. Our final answer is going to be the estimator is equal to y bar. Now, why does that make sense? What we're saying here is if you're assuming that your model is that the slope between x and y is 0, that your points just look like this, if your model really is that the slope equals 0, what's the best thing to show that relationship? Well, it's a line with 0 slope. All right, let me change color here. A line with 0 slope with some kind of y-intercept. What should you choose as the y-intercept? The average of the y values here is what that's saying. So these are two quick degenerate cases, we might call them, where you're not looking at a real y-intercept, a full model with a y-intercept and a slope. We looked at one case where we assumed the y-intercept was 0, another case where we assumed the slope was 0, and we got a couple of interesting results here. So hopefully by looking at this, it'll help you understand even better the derivation and the rationale behind the derivation of the OLS estimator for the full model with a y-intercept and a slope. Any questions? Leave them in the comment section below.